Hi, this is Wireless Future. I'm Eric Larsson, and I'm here, as always, with my colleague, Emil Björnsson. Hello, Emil.
Hello, Eric. How are you today?
Good, Emil. How are you this cold winter day?
It's great. I'm inside, fortunately. So even if it's cold outside in Sweden this time of the year, then it's still okay inside.
Not feeling the biting cold inside of the studio. So,
No.
What's hot? What's hot, Emil, in 6G?
Right. So for the last 2 years, I've been the online content board chair of Communication Society in IEEE. And then I got the work task of looking through all of the keynote speeches on the big Comstock conferences like ICC and Globecom and how to sort of suggest keywords for those ones. And then I realized that many of these particularly industry key notes are covering basically the same different topics. There is some AI there, but in particular there is a lot of ISAC, integrated sensing and communications.
You're saying there is some AI there. I thought there was a lot of AI there, that everybody was talking AI, no?
Yeah, everyone talks AI and everyone talks ISAC.
Everyone talks AI and everyone talks ISAC. So
then writing keywords that should help viewers to distinguish between the different videos became a little bit redundant than when it's 6G, AI, and ISAC everywhere.
So that trio combination. So today, I think ISAC.
Yes, today we take ISAC as a topic.
So ISAC stands for Integrating Sensing and Communications into the networks, into the actual 6G standards and systems. So when we say communications, of course we all know what we mean. When we say sensing, how do we define that? Is this like classical radar technology or is it something else?
Yeah, it's a type of radar technology. So radar stands for radio detection and ranging, and that was an abbreviation that was made almost 100 years ago. But already since the beginning of wireless communication, people have also used wireless signals to bounce them on objects and observe them elsewhere and try to detect what is going on. Is there a reflector somewhere? How is it located? How is it moving? And so on. So we can detect the objects, we can detect the range of those objects and whether they are moving and maybe track them on a map, for example.
So objects here would be like anything that moves around in the network. Could that be like users also, or would it be more like objects that don't participate in the actual communication, like cars on the street and drones in the air and that sort of things? Or what is like the primary thing that one would want to sense and detect here?
So in principle, it could be all of the things that you mentioned. Often when we talk about sensing, it is something that is not currently radiating the signal that we are considering. So it could be, of course, a user device or a car that the user device is sitting in, but it's sort of something that becomes part of the echo of the signal. So the signal bounces on objects, and then the communication channel, or the channel in general between transmitter and receiver, is a combination of all of those echoes. And then we can see what are the delays of different echoes, and they are representing objects, and are some of them moving across time. Well, then the echoes also change their properties over time. And so it's typically anything that is big enough to become a substantial kind of echo that we can distinguish from the other ones.
Right. I mean, I can imagine in 6G, I mean, if we just look at the baseband interface, there's so much data available. We got like 100 megahertz bandwidth, perhaps even, and so you sample with 100 megahertz or something sampling frequency, then every second you get 100 million baseband samples per antenna, which could be used to infer a lot about what's going on within the environment. But if we think radar, which I think was really developed during this and after the Second World War, then that has turned into a fairly mature technology that's now used for all sorts of purposes. I mean, anything from airspace control to synthetic aperture radar imaging to radars on cars to measure the distance to avoid collisions and so on. So what is really new with the ISAC technology in that, in light of that?
Right. So the radar technologies that you are describing are things that have been developed dedicatedly for radar purposes and deployed in a number of different scenarios. The intention with ISAC is to add sensing into the communication systems that we are deploying, the type of cellular networks that 5G and 6G and so on is referring to. And that can be integrated in a number of different ways. The first integration level would be very soft. It's just like the telecom operators, wherever they put the base station, they also put a dedicated sensor that can be used for radar sensing. But its two systems are entirely different, just co-deployed.
Oh, so stop and let's break this down. So then you're saying that basically the only air quotes integration here between the systems is that they share the same tower or the same site, maybe the same power supply, but they're really like completely different systems. There is a wireless base station, and then next to it there is a radar unit. Is that an accurate understanding?
Yeah, so that's the first kind of integration level.
I mean, to me that doesn't sound like a lot of integration, really. It sounds more like you make a deal with a site owner that you can put some additional gadgets in the tower.
No, exactly. And it might not be the most attractive option either, because many of the wireless radios that we're using at the base station today, they are capable of transmitting over a much larger frequency spectrum than a typical telecom operator is allowed to use due to spectrum licenses. So therefore the second integration level will be that you build radios that are wide enough so that you can have one frequency band for communication and another one for sensing, and you can use them simultaneously. Same hardware, but different frequency bands, so the systems are not really interfering with each other.
So basically what you're saying is then that you've got your 6G base station and it samples a wide enough bandwidth so that you can actually over the band that you take into your digital interface, you can use parts of that band for communication and another part for sensing. But would that sort of like multiplexing between sensing and communications, would that happen all at baseband, or would there be separate baseband units with sharing the same antenna, or at what level would this kind of split happen?
Right. So at the lowest integration level, this would be two separate bands. So I think today there are some parts in the 3 gigahertz range that are used for 5G and some that are used for military radars. And if you would bring both of those into the same hardware, you build an antenna that can handle the entire 3 gigahertz band, and then you pull out these two different parts, but maybe you do the signal processing for each band separately because they're actually separated.
I see. So you do the signal processing separately. So it's not like you sample the whole thing and then process the samples in one way for the communication purpose and in a different way for the sensing. Because one could also think of that.
Yeah, so that is one option. And what you are describing is the third integration level, where you say, here I have a spectrum license, I only have one band, I will use it both for communication and for sensing. But to protect these two applications from each other, I will be dedicating certain parts of the frequency band for the sensing, a certain part for the communication, or particularly you could also switch in time between things. But the important thing is that you have like orthogonal resources in time or frequency, some for sensing, some for communications, and then you operate your system. But then you need to take out the entire signal and turn it into baseband samples and do the signal processing to really pull them apart.
I see. So now we are at the third integration level. So basically then you get a bunch of baseband samples, and then you multiplex the communication activities and the sensing activities orthogonally, either over frequency or over time. Got it.
And then you can take it one more step, and that would be that you use the signals that are actually meant for data, and you let them bounce on objects as well and observe the received echoes somewhere, and then you use that for the sensing. So you really do the sensing and communication at the same time, at the same frequency, and it potentially, when we are often using directional transmissions using what we call beamforming, we could send a signal in one direction to a user, another direction to another user, and then we can have somewhere in between where we are sweeping around a known radar signal in order to observe if there is anything in between the users. So that would be the deepest kind of integration.
That would be the deepest level of integration. So basically you're saying that if you got a lot of antennas like in MIMO or massive MIMO, then you could communicate in some small subspaces where the users actually are located. And then in the rest of the space, like in anything that's orthogonal to the subspaces where the users are located, you could do other things like send sensing or radar signals, for example. So these are the 4 levels of integration. At first level, just sharing the site, separate equipment. Second level, use the same frequency band and maybe the same antenna, but you kind of take the signal, you split it into 2 different channels that are processed completely separately. And the third level of integration, so basically one antenna, one RF chain, you get a bunch of baseband samples, you multiplex the sensing and communication activities using time division or frequency division multiplexing. And the fourth level of integration, you perform the sensing and communication simultaneously in time and frequency, but you separate them spatially using different kind of beamforming techniques so that you can beamform to a mobile user at the same time as you are beamforming power to scan some maybe angle into the sky or somewhere.
Right.
Cool.
So that is a correct description, and I think a lot of the academic works on this topic are considering that last, the most deep integration, because people who are doing theory often are coming to the conclusion that if you want to do 2 different tasks, if you allow them to be done simultaneously, you often have more degrees of freedom in how you design your systems as compared to sort of forcing them to be orthogonal. So in many cases that also shows mathematically that under ideal circumstances it is best to do 2 things at the same time and then fine-tune things so that both tasks works out well. But I believe the industry might start with a third integration level where you are distinguishing between sensing and communication by orthogonal time frequency scheduling.
Sure. I mean, this fourth level of integration really sounds most exciting to me because the first 3 levels sound more like different ways of building the electronics, which in itself, of course, is an enormous challenge. But from a academic research perspective, it sounds like developing beamforming algorithms would be maybe like a little more deeper and interesting as a topic. But I could also imagine that there must be like a lot of fundamental trade-offs here. For example, if we beamform a signal to a user at the same time as we illuminate other parts of the area or the cell in order to detect the target or something, then we have to split our output power between these 2 activities. And sensing fundamentally seems to me is limited by power, by the link budget. So it's not obvious that it's necessarily a good idea to not use all the available power for the sensing, but use some of it for communication at the same time. I mean, there seem to be like a host of non-trivial trade-offs here that I'm sure have been studied in many papers. All right.
Yeah, no, you definitely have the power trade-off that you need to split between these different tasks. And then there will be interference if you do them at the same time or frequency. If you have very good knowledge about some of your communication channels, you might be able to separate that interference, and ideally this is what leads to conclusion that you want to do both things, that optimal trade-off thing. But in practice there's a lot of uncertainties in your system that makes it still easier to build things in an orthogonal manner. So I think that industry will do that first and then maybe go into the deepest kind of integration if it works well.
I see, sure. I mean, another thing I can imagine is that when we communicate, then we send pilots typically, right, to get channel state information. And this channel state information is used to demodulate data. It's also used for beamforming and so on. But in sensing, we got no data to send, but we rather send known reference signals, let's call them pilots, to probe what the environment looks like. So it seems to me that in a comm system, the pilots are just like an unnecessary overhead. That we put them there, we use them, and then we just use the result. But the pilots are not what we're interested in. The channel state information is useful, but it's not what we ultimately care about. But in sensing, it is the channel state information that's the end goal. Is that an accurate understanding, or how would you describe the difference between like using a wireless signal for comms versus using a wireless signal for sensing?
Yeah, I think this is an accurate description. So whenever you send a wireless signal, the receiver will get a distorted version of it, containing a number of different echoes, which are time delayed differently and have different amplitudes. And when you want to communicate, you just want to get rid of that distortion. So therefore you send this pilot that you described, you estimate some parameters, which might just be some complex numbers with an amplitude and a phase. And then at the receiver, you do some equalization while you're sending data. So you basically take the received signal, try to undo the distortion as much as possible, and then after that you're only interested in the unknown data that was sent. So you basically need to send a known pilot signal so you can learn the channel to the some mathematical coefficients, and then you send data once you know these coefficients. But in sensing, we're only interested in those coefficients, but we also want to dig deeper into the meaning of those coefficients. What are the objects that give rise to those specific numbers? And that is what the sensing is all about.
Yeah, so I can imagine for sensing you need a lot of bandwidth, because bandwidth is what offers us time resolution, right? I mean, if we think of just sending a pulse and then measuring how long it takes for that pulse to travel to a target and get reflected at the target and come back, then the accuracy by which we can measure the time delay and of this transmission of the pulse, and therefore the range to the target, will be proportional to how narrow is the pulse. And the narrower is the pulse, the more bandwidth it will occupy. But I suppose you also need time resources for sensing, don't you? I mean, it's not enough to just send a short pulse. In some cases, you actually want to send a signal that keeps going for a long time. Is that true?
Yes, exactly. So that is the basic scenario, which is called pulsed radar, that sends just a short pulse, and the shorter it becomes, then when you get it back, it will be easier to sort of, when you sample your signal, discover exactly where was the pulse, where's the middle of the pulse, and where is the rest of it. And then we have this kind of trade-off that if a signal should be very short in time, we need more spectrum in the frequency domain. So that is one thing. And so the range resolution comes exactly from what you were saying. We send a short pulse, we see when it comes back, and then half of that time is how far away the signal were, and then you divide with the speed of light and get the distance. But if you then also want to figure out how this target is moving, then you are using a phenomenon called a Doppler effect, which says that depending on if the signal or the object is moving towards you or further away, that will shift your frequency. And what that would lead to is that if you are sending the pulse multiple times and repeat it with a particular time interval between them, then when you are looking at received signal, the time between the pulses will shrink or increase depending on that Doppler effect. And that allows you to sort of estimate also the velocity of the moving target, and from that you can calculate those type of parameters.
Right, so I guess one way of understanding this, again, that we want a narrow pulse, to get the time resolution, and having a narrow pulse requires a wide bandwidth. But then to estimate the velocity of the target, then essentially we want to estimate the Doppler frequency. So we want to estimate the frequency of a sinusoid. And to estimate the frequency of a sinusoid, it helps to observe that sinusoid over a longer time. So that's why we need the long time to get the velocity estimates. But in addition to frequency resources and time resources, I imagine that multiple antennas, MIMO arrays, are going to be immensely useful also for sensing. Of course, MIMO has been one of the major breakthroughs that made 5G possible, and spatial multiplexing in particular possible. But it seems that it might be even more important for sensing, because with a MIMO array, you can really look into distinct directions into space. You can parameterize your transmission through azimuth and elevation angles. Could you speak to like what type of MIMO processing that's envisioned and which is to be used for these sensing activities?
Right. So this is a very important aspect here, and there are multiple parts of why we need the MIMO technology. One of them is because you want to know not only how far away and at what speed the target is moving, but also know in what direction it came from, because then you can really position it. So with beamforming, so you use your antennas to send a spatially narrow signal in a particular angle or direction, and then observe from what angle the signal came back, which in a scenario where the transmitter and the receiver is the same location, it's the same angle then. But that allows you to sort of get this information out of it. But then the other aspect is that when you compare a radar system with the communication system, in communication you just need to send from one point to a receiver. But in sensing, you need the signal to go to the receiver or this other location and then come back again. And that creates like a twice propagation distance, which leads to a substantially larger propagation loss. And that's the reason why we need also this kind of directional transmission to keep more power, get the higher signal to noise ratio.
It sounds a bit like in communications, right? Do you want a large array of antennas in order to get a coherent gain or an array gain to improve the link budget? And you also want a large array of antennas or the large aperture in order to be able to form narrow beams to pinpoint a specific location in space where you want to beam your signal to your terminal. But of course, a core difference in sensing is that the path loss multiplies. This is basically the radar equation. You got the path loss to the target and times the path loss back from the target.
Yes, exactly, and that is a much worse propagation condition, as you were saying. And just to give the sense of it, you don't add up the distance to and from the target, but you multiply them together in your equations. Yes, then the fact that you need to use multiple antennas or radiating elements to do beamforming, this is something that has been well recognized for a long time, and that this has been utilized in communication and sensing a lot, but the technologies have to some extent evolved differently, but it also builds on the same basic characteristics. So one can talk about 3 different sort of stages in this evolution. So the basic thing is in a base station of the 1G to 4G times, we used so-called sector antennas, which are directional transmissions, but it has a fixed pattern. It covers like 120 degrees, so 1/3 of the world from a base station viewpoint. The user is supposed to be there, and you are just beamforming the signal down in a fixed way to where the users are supposed to be down on the ground. And the equivalent on the sensing side is that you have a sensor that only looks in one direction, or you have this fixed sensing direction, but then you start rotating it in a mechanical fashion. And that is something that many people have seen on boats. You have this kind of panel that is on the top of the boat that is rotating and is all the time sweeping around and look in with the fixed beam, but in different directions to see if there are any other ships on the sea. Then we know that if we have a collection of antennas, we could phase shift the signals from those antennas in different manners in order to electronically, without physically rotating anything, we can change the beam direction. And we can at least do this on one side of the array. And this is technology that is also used for both communication and sensing. In communication, this is kind of the simple case. If you only want to send one signal, you can change the beam direction. It is used in base stations for so-called electrical tilt to determine how far down the signal should go. And it's used in the millimeter wave system today for so-called analog beamforming, where you are following a receiver by just sending one beam. And then it is used in some semi-advanced sensor radar systems, where it is called a passively electronically scanned array, or PISA, where you can follow targets or search them in different directions. So if one looks at the military radars that are used in Sweden today, they are of that kind. They are mechanical rotating, but they can scan signals up and down and look for aircraft, for example. So a lot of countries are using such kind of systems. And then one can take it one step further, and that is what we are using in 5G today on the base stations. We have antenna arrays that are not only possible to change their phase shift so they can send one beam, but they can send multiple beams at the same time, and they can fine-tune it so it doesn't even have to be angular beams. And this is what we, for example, call multi-user MIMO or massive MIMO, and we can send these kind of things. And at the radar side, these are called active electronically scanned array, or AESA, and that is really the sort of state-of-the-art also in military radars. And what can you do with something like that? Well, in communication, you can serve multiple use at the same time. In radar, you can sense and detect multiple missiles or other things at the same time from such a radar. So in a way, one can say that when we are taking a 5G base station, turn it into 6G, and add this kind of sensing capabilities, it has to a large extent similar characteristics with this multiple antennas that you can control individually as a military radar. So it can really be a very advanced type of radar from that viewpoint.
Right, so what you're saying is a state-of-the-art radars basically use an antenna array, just like in massive MIMO, where every antenna has its own RF and baseband chain, and you can phase coherently process all the samples and form beams both on transmit and receive. Sure. So I mean, given that, it sounds like integrating sensing or radar functionality into 6G wouldn't be that hard. I mean, at the surface at least, because we already got these antenna arrays, we got the RF and the baseband, and we got the ability to send the individual data or waveforms through each one of the antennas. So where lie the challenges in integrating this sensing technology then, really?
So there are two particular challenges, and one has to do with this kind of path loss that is much larger. And if you compare the arrays that are used for communication and for military radars, for example, then there is a large difference in transmit power. So a typical base station in 5G might be transmitting with some 200-300 watts, while a military radar might use 200-300 kilowatts. So there's 1,000 times larger transmit power there.
I mean, just to appreciate the difference, 200 watt versus 200 kilowatt, that's 3 orders of magnitude. Just imagine the amount of heat that's generated and dissipated in the electronics, and just imagine the power supply that you need for a 200 watt transmitter as compared to a 200 kilowatt transmitter. Sure.
Right, and I picked this example because there are systems working in roughly the same frequency ranges that have these type of numbers today. The other thing is that when we are building our communication systems, we typically do transmission and reception separately. So 5G systems are typically time division duplex, where you transmit and receive on the same band, but you switch of it in time. Or there are some systems, the particularly older system, which are frequency division duplex, and then you transmit and receive in different frequency band, and that you can't so easily integrate radar into that kind of system. In the TDD case you can, but then you need to sort of either have a situation where every base station has both a transmitter and a receiver, so you need more hardware, or you need to have a situation where you transmit from one base station and you receive at another base station, which can then not transmit at the same time. So there are some complexities related to how you build that kind of system as well.
Yeah, I can imagine. I mean, so for sensing, you either need a monostatic setup where the transmit and the and receive array are in the same array, so then the electronics have to be full duplex, or you need a bistatic setup where one array transmits and an array somewhere else receives, and that seems to me that it would integrate quite naturally into TDD in for communications. But also now, given that we might want monostatic sensing using one and the same full duplex antenna array, both for transmission and reception, and given that we need 1,000 times more output power, that this integration is going to be nearly impossible. But maybe that's not how.
Yeah, no, so there's definitely a lot of implementation challenges related to something like that. So one thing you could do particularly when you build this kind of pulsed radar that we were talked about earlier, where you transmit pulses occasionally, is that you transmit with your entire antenna array, and then you quickly turn it into reception and wait for the echoes to come back. And that gives you some kind of blindness for very close by targets, because you need to have some switching time, but otherwise you don't need to isolate transmission and reception because you switch like that. But since we want to communicate most of the time as well, we can't really do that in a 6G system. So for that you probably need to have a dedicated transmitter and receiver at the same site, and then you need to do a lot of effort to isolate them to build this kind of full duplex systems, and that is not something we are used to do today, but in principle we could do that. People have been able to build full duplex systems. The other option is what you call the bistatic scenarios, where you would still have base stations with similar kind of hardware as today, but you just choose some of the base station to be receiving when the other ones are transmitting in the downlink, and then that would solve the problem. You don't need to full duplex hardware, but the difficulty is that then you need to make these two base stations share information with each other. They need to know what signal the other one is going to send and when, and a lot of coordination and synchronization between these different base stations.
Yeah, sure. I mean, but now, as you said, a typical like military radar uses a lot higher output power. I suppose we're talking about average output power here, because what matters for radar is really power multiplied by time, also energy do you spend on a specific detection task. But I could also see that, and in that context, or in comparison, then a 6G base station would be at a serious link budget or SNR disadvantage. But I could also see that these 6G base stations would be deployed a lot more densely, so that distances are shorter, and then perhaps a much lower output power might be required. So we don't need the same range, therefore the path loss is less, and the requirements on power is also less. But could you speak to that?
I forgot to say earlier as well that a really state-of-the-art military radar is also physically larger, have more antennas than a 5G or 6G base station would likely have. So you have disadvantage both in power in terms of number of antennas. But the hope is that instead of having like a few of these radar units that are scattered over the city or over the country, and you are hiding them so that it is hard for someone to know exactly where they are, but they have enormously long range, then instead you build a system where every base station in this entire country could work for ISAC, and then you don't need as long range. And I think some of these kind of early warning radar systems that the military are using, they are meant to have some 300-kilometer range, and if you cut that down by a factor 100, which will require like a link budget that is substantially less than as well, then yeah, you can do ISAC within a few kilometer range, and that could be enough to do some new things that we couldn't do before.
So basically you're saying that the 6G base stations, because they're so densely deployed and the distances for sensing will be so short, that the output power that they have will be sufficient, like a few 100-watt perhaps. But I could also see that the 6G, or at least the 5G base stations, are tilted in a very specific way. So for example, if the objective is to detect something up in the sky, then the antennas are just tilted the wrong way, are they not?
So that's true. So base stations of today, there is a typical approach that you, instead of deploying them in a vertical manner, you tilt them some 5-10 degrees physically downwards, because you expect your users to be underneath, and you also want to help the base station to isolate itself from other cells, because there will be other base stations that cover different regions. That's why you don't want to sort of aim the strongest direction toward the horizon, but slightly downwards. But when you have a massive MIMO system, you still have the possibility of electronic beamforming up and down. So even if you are physically have your main direction 10 degrees downwards, then you can still search upwards. And it seems like these kind of systems also will be able to explore part of the sky. I wrote some papers some years ago, which was more about, can base stations with down tilt serve drones more from a communication perspective, and the answer is yes, you can get that kind of range. And interestingly, it's often so that when you are aiming into the sky, you have many base stations that can see the same coverage area in the sky, and that is helpful from ISAC viewpoints, while when you transmit downwards, there are objects blocking down on Earth, and from that viewpoint, the coverage is much more limited down there.
Yeah, sure. I mean, but I insist that even the massive MIMO panels are tilted slightly downwards, right? And you're right, you could definitely configure your MIMO weights so that you beam a little bit of power up into the sky, but it would certainly help if the panel itself were not tilted so much downwards, but more like flat, or pointing towards the horizon, or even a little bit upwards, or if the panel was redesigned so that more power could be beamed up into the sky. Because fundamentally, at the end of the day, sensing performance will be limited by the link budget. I mean, that will determine how far away targets that we can discover. It will determine how small targets in terms of radar cross-section that we can detect and discover.
Right.
So there seems to me to be a bit of a fundamental mismatch between the notion of down-tilting antennas for the purpose of building efficient cellular wireless systems and beaming power up in the sky for detecting something that's flying there. But anyways.
Yeah, no, so that's certainly true. There will be a trade-off when it comes to the deployment of flat panels, depending on if you want to communicate or sense things on the ground or up into the sky. Then one should say that a panel typically have some kind of scanning range, which is plus minus 60 degrees, so 120 degree sector. And if you then tilt it up or down some 10 degrees or so, you shift some of the scanning range, you take it away from upwards and provide it downwards. But you will still have the substantial scanning range up into the sky, I think.
Yeah, maybe the panels shouldn't be flat. Maybe they should be curved, like this curved, but of course curved this way.
Yeah, right. And that one can see maybe at some airport or places like that as well, where they have this kind of more spherical looking shapes that are very advanced radar system that have a 360 degree view of the world.
Right. I mean, of course, radars like that exist, but I meant for the 6G panels should not be these flat panels that we built for 5G.
Yeah, maybe we should have some other shapes in the future.
All right. Yeah. So now, in terms of applications of this ISAC technology, I can see that detecting like flying objects, maybe drones, that would be like one potentially important application. What else?
Right, so that is definitely one of the first things that comes to mind, that detecting drones flying around over the city in a way that they're not supposed to be, or see other things in the darkness. But I would categorize the use case of ISAC into two parts. One is sort of an internal way that inside your system that is mainly built for communication, you want to improve how you operate. And then there is the external part, which is about doing things that can be useful for external applications. So if we start with the internal part, one thing you can do is to track users. So we can imagine, there is someone sitting in the car here and they are watching a YouTube video from their favorite channel, and then they are watching continuously, but actually the data and transmission is not continuous, even if it views like that from the application layer. So when you are switching between serving the user and not serving the user, you could use your system to track the user in between and sense the type of things. And this will be helpful for know where to point your beam and how to sort of hand over from one base station and so on. So these are some things that you could make more efficiently. You can also think about that a base station could sense what is going on in a neighboring cell, so it can make some kind of interference suppression more effective between the cells, for example. Or we can just use this as an additional input to position different users in a more effective manner. So all about operating your internal system more effectively, just make the communication better for the amount of money that you need to spend in terms of deploying the system. So does that sound attractive for a telecom operator?
Yeah, I don't know. I mean, again, I can appreciate this kind of public safety, let's call them public safety applications, where you want to sense if there's a drone hovering somewhere or flying somewhere, or you want to maybe sense traffic on the road. I'm not sure, but I'm not sure I completely understand these other more internal use cases, because to me they seem to be problems that can be solved just by sending appropriate pilot signals, and that wouldn't really be sensing. I mean, of course you could call it sensing, but let's face it, that's the standard pilot transmission, and then the network acting upon and inferring from those pilots what to best do. So to me it really seems that at least if sensing means broadcasting or beamforming a signal that get bounced at some object which is not actively interacting with the signal, but the signal just gets bounced or reflected there, and then measuring the reflection, that would be primarily for detecting objects of some form that aren't communicating nodes to start with. I mean, could be a drone, could be something driving or flying along the road, or something of that sort.
Right. And that, of course, takes us over to the second category of more external use cases. And maybe that is where standardization of these type of features becomes more important, because some of these internal things, you can find some clever proprietary algorithms that you deploy in your system without actually having to tell anyone else about it. But externally, yes, surveillance of different kinds for public safety, for drones, or see how much traffic there is, could be useful. That could also be fed into a number of different systems. You can have some kind of smart city optimization where you want to monitor the traffic on roads and maybe control the red lights or steer traffic in different ways.
I mean, isn't it that traffic on the roads is the network already knows, because Google already knows where the traffic is, because everybody's carrying a cell phone, and the cell phone is basically sending all the time some sort of reference signals or packets or pilots. So it is already today a reality that we are tracked when we are driving on the highway, and all these data points can be aggregated to see where are the traffic jams and where is the traffic like flowing versus not, and so on.
Yeah.
So that application is only marginally convincing to me. I can see the drone detection use case, but I can also see that, I mean, it feels like this could easily evolve into a cat and mouse game where the base stations are able to detect drones in certain parts of the sky, but there will always be blind spots, and those blind spots ought not to be too hard to compute where they, or calculate or explore and discover where they are, and drones could like fly that's under the radar and just hide in spots where the 5G or 6G coverage isn't sufficient. Has anybody really done like any serious system level calculations on how big part of the sky is possible to guard or protect or survey versus not, insofar as drone detection is concerned? Do you know that?
I haven't seen any such calculations. Maybe they exist. What I've seen are some examples of how real base stations have been deployed and data have been collected in order to observe what is going on down in the city and see both drones and cars moving on the highway and things like this. So such proof of concepts exist, but I agree with you. It's more interesting in situations where you are detecting objects that doesn't carry a mobile phone connected to the internet that is anyway sort of feeding information into Google or Apple or something like that. Then one can of course consider also from the safety viewpoint there, or for the integrity of the data, who owns this data? Well, the telecom operator owns it and can sell it. They are not sort of dependent on a hyperscaler to collect something. And if someone wants to hide and drive around on the highway without having a mobile phone telling Google where it is, well, then you also get that kind of information.
That's right. But at the end of the day, I mean, someone's got to pay for all this, right?
Yeah.
I mean, could you imagine that society might be willing to pay for public safety applications like keeping track of drones, for instance? But for the traffic on the highway example, it's less obvious to me because, I mean, Google already has the data, already knows us. So would we want to pay twice and then use this sensing technology to figure out again where the cars are?
Right, and this is one of the big challenges when it comes to all of the applications in cellular networks that goes beyond just data communications. And it has been one of the reasons why the deployment of standalone 5G that enables you to do new things beyond data communications have sort of gotten very slowly. In principle, if you upgrade your core network so you get a standalone 5G network, then you could change the reliability and energy performance and so on of the system. You can build new applications that are sort of talking to the network and extract different kinds of data that is already in there, and make your applications more aware of its surroundings, and their ISAC will be part of that. But yeah, the difficulty is to convince someone to pay for it. It looks now like the standalone 5G deployments are to a large extent pushed in the world due to government saying that we want it just because we want to stay ahead and hope that new use cases that are commercially viable will appear, or we want it because of public safety reasons. And for the same reasons, ISAC might be pushed also first from governments wanting to pay for these functionalities, and then maybe other use cases can also be commercially viable.
I see. Yeah. So what are
but one can of course just throw in a number of different things that people are doing in presentation and say all this data can be sort of thrown into a digital twin or whatever we want to be, a city, a factory, a workplace, and then the digital twin will predict how the building works more effectively, and you can do all kinds of optimization of your resources. But it becomes very vague. Is it actually ISAC data that you want to feed into a digital twin to control the system better, or is it something else?
Oh, well, so let's talk a little bit about the technical challenges of making this work. I mean, now, given we already got MIMO, we got massive MIMO, we got these big arrays, we got RF chains, we got digital signal processing, processors, and so forth. On top or in addition to that, what will be required to perform sensing? I mean, I can imagine, for example, that phase synchronization, at least in bistatic setups, could be an important thing. Calibration of antenna arrays, if you want to send like beams into specific angular direction, that sort of things would be totally important, and maybe even the critical, maybe even the weakest link in the chain, perhaps. But in addition to synchronization and calibration issues, what else would be what other technology components would be critical to develop, and what problems would be critical to solve here?
So what you described are challenges that are there already in communication systems of today, and I think to some extent 5G systems are relying on that you have some kind of array calibration, so you know what angle you want to transmit in, because the code books for feedback of channel state information is built on that. But it might very well be that the people building the base stations have been cheating a little bit with how accurate that kind of calibration actually is, and they can get away with that. But if you want to really do sensing, they need to really take this kind of thing seriously. And yeah, the bistatic scenario is even harder because you want to synchronize two different sites, and apart from those aspects, I think one of the big contentions is what kind of signals will be transmitted for sensing. The first step is to just keep the same kind of grid of transmitted signals we have today, which contains a collection of reference signals, and then you have some data signals in between there. And the reference signals comes in different bursts. Sometimes they are spread over the frequency to enable channel estimation, and sometimes they are used for localization. And that kind of collection could be used for some kind of sensing. But if you want to modify the standard and send other signals that are specifically good for sensing, and what do we mean then with sensing? Should it be good for range estimation or Doppler estimation or something else? Yeah, those are some of the things that are discussed a lot.
Sure, but I mean, okay, playing maybe the devil's advocate for a second here now, isn't all of this well known? I mean, isn't it known that for radar sensing, you want a waveform with a good ambiguity function, and that sort of waveforms have been developed and are being used by radar systems. And for comms, we want waveforms that are attractive to deal with from an equalization complexity point of view, and then the choice falls on OFDM with a cyclic prefix, typically. So what is really like what are the new questions here in waveform design?
Right, so the ambiguity function, which is sort of giving you a basic description of how well you can estimate delay and Doppler, these different ambiguity functions have different characteristics for these two different use cases, because they also have some internal trade-off between each other.
Oh, of course, there's always a trade-off, yeah.
Exactly, and where, for example, if you just send a sinusoid on one frequency, that and then that would be quite useful when it comes to see how that one frequency is shifted. So it's good for Doppler, but it give you no time reference to know what was the delay, because the sinusoid is just repeating itself, right? And then you can design something else that also provides you with the range resolution, and there people have been having, for example, the idea where you take that frequency and you are modulating it, so you're varying it up or down, create what is known as a chirp, and then you get some information about that. And if you take those waveforms that people have designed for radar, then you compare it with the OFDM that we already have, and we see that there is a mismatch there. Then there becomes a discussion, should we change the waveform in 6G to adapt it to the ambiguity function for delay or Doppler estimation to make it better?
No, sure. I mean, but nothing, I guess, prevents us from. Now, if we want to integrate sensing functionality and use some of the frames for sensing, those frames could use some other modulation format or a waveform format than OFDM. You could throw in a chirp, for example, if that's what you want to have there, or something else that gives you good ambiguity function. And then when you go back to communicating, you revert again to OFDM operation.
Right, and ideally you want to not have to redesign your hardware too much, but do this in a software controlled manner if you can. And one way of viewing this kind of chirps is that if you have a block of time and frequency where you send multiple subcarriers, a chirp is basically just gliding between the subcarriers in a continuous manner. And then there are some people designing multi-carrier waveforms where you say instead of just sweeping between the different subcarriers, you have multiple of those ones that are sort of gliding between the subcarriers in a so you get the multi-carrier chirp kind of system. And the latest thing people talk about that is called AFDM, Affine Frequency Division Multiplexing.
Okay,
and
affine frequency division multiplexing. Yeah, sounds like something we should read up on. Okay, yeah.
Exactly. So I think 3DPP has decided that OFDM with cyclic prefix will be sort of the base thing for 6G, but one can certainly do, as you said, pick out a certain time frequency block and send something that looks like a different waveform there in order to adapt for sensing. And yeah, one of the people are pushing for that. They often are saying that Doppler shifts are difficult to handle. If you want to find reliably fast-moving objects, then the subcarriers in OFDM, they are breaking down. When you shift in frequency, they all get mixed up, and that breaks the orthogonality and everything like that. Right. While this kind of chirps, that they are shifted in frequency due to the Doppler shift, but they still keep their pattern of how they are gliding between frequencies, and that should somehow make it better.
That's right. I mean, so in a way, we're going back to the classics here, because chirps have been around for decades, and like the standard waveform in radar systems.
No, exactly. And it's actually so that already some 10 years ago, when there were discussion about what waveform to use in 5G, there were another waveform that a lot of people talk about, OTFS, orthogonal time frequency space modulation, and we talked about this in a previous episode as well to some extent. And so the industry have been looking into for quite a while, is it beneficial to change the waveform or not? And they seem to be not that hot on this, because maybe the use cases when it really makes a difference what waveform you have is kind of extreme as well.
Yeah, I mean, OTFS, I guess, fundamentally probably is superior, but the advantage is very slight unless you have very high Doppler, unless you see in very high mobilities, you see very high Doppler frequencies. And then, I mean, also on top of OFDM, you can build a lot of processing, right? You can build OFDM with processing across the blocks and essentially achieve the same thing. And of course, as we know, OFDM has that super advantage of n log n equalization complexity by virtue of the cyclic prefix. And I think it should also be pointed out that in OFDM, there is no fundamental reason for throwing away the samples that we gather during the cyclic prefix. We do this, but we do it only for convenience, only to get the n log n equalization complexity. Nothing prevents us from keeping those samples and run a maximum likelihood decoder, in which case OFDM would of course would also improve performance-wise.
Right. Yeah, and if one reads papers about these waveforms also from a communication viewpoint, one thing they are saying is that when you have a multipath channel, one typical thing that happens is that over the frequency domain, the channel is going up and down in quality, because we get some frequency selective fading. And then in an OFDM system, that means that some subcarriers becomes bad and some are good, and you have to live with that. While if you are using this kind of more chirp-based kind of waveforms, they are shifting over the frequency domain when they're sending, so they are all sort of gliding between the good and the bad fading realizations and get something that is more on the average. So from that viewpoint, people like to say that, look, these waveforms are providing more diversity against fading. But of course, if you have a multi-carrier system, you also get similar diversity against fading by just spreading a channel code over time and frequency as well. So there is a risk, and I think that is what has been happening, that people are focusing on very specific properties and they're overemphasizing this, but at the end, when you build something, OFDM is still quite good.
All right. So in the end, what is your vision, Emil? How do you think a typical implementation of ISAC will look like in 6G?
Right. So I think that ISAC is one of the features that will be there from day one in some form, because everyone in the industry is talking about this. And I think the basic thing would then be that by 6G, everyone will have standalone networks, so you can implement this on a lot of different base stations. You will start with some kind of either bistatic scenario where you are turning some of your base station into receiver mode when the other ones are transmitting in the downlink, and that gives you some information that you can try to extract in order to do some basic sensing. And you then want to sort of typically it takes a few base stations that have overlapping coverage area so they can see each other's users or targets, and then they also connected to the same baseband processor, so it's easy to share the signals there. And then probably reference signals that are already there for channel estimation, they will be reused and potentially modified a little bit so that they enable sensing. But one will probably also open up the door to have some more variations in the reference signals depending on how much sensing you want to do in one place compared to another one. Then I personally think that an attractive thing would be in the cities to go from just deploying on a rooftop, like one panel pointing in each of 3 different directions to cover an area, and instead have multiple panels pointing in the same direction, but moved by a few meters apart, so you get some natural separation, and then you can use both of them to transmit to users for communication viewpoints, and then you can improve the capacity and distinguish users better. But you can also, when you want to do ISAC, let one of them transmit and the other one receive, and then you get some monostatic like setup. And it's much easier to synchronize things that are just a few meters apart from each other.
Yeah, that's true. But hey, wait. I mean, if you put 2 panels there, if they are separated, I don't think that will be a monostatic setup any longer. Then it's bistatic, but they sit very close. And if they are really very close, so that you can argue it's monostatic, aren't you going to get like a lot of direct link interference between them, even though antenna patterns don't like... Of course, they don't point towards each other, but they will always be some. the antenna pattern will always leak a little bit.
Yeah, so you need to definitely work there with the isolation and the deployment and everything like that.
Yeah.
And some kind of self-interference suppression will probably have to be done as well.
Probably have to be done, but you're right. I mean, it could be driven by one and the same clock easily, so that you synchronize them in time and frequency and phase through that. Yeah.
So, and this is of course a first step. If this works, then it would also be a first step towards what we have been talking about, cell-free or distributed MIMO, where you would like to distribute your antenna panels even more, both for communication viewpoints, but also for sensing. And sort of the most advanced type of sensing is a multistatic sensing, where you have one transmitter and you have multiple receivers that are then collaborating and detect things together. So there are possible ways of this could evolve into the future.
Absolutely. Yeah. Yeah, great. Thank you, Emil.
Thank you. Always nice to talk to you about various topics that are happening in wireless communications.
Indeed, it is. All right. And to the audience, don't forget to like and subscribe to us on YouTube and Apple.
Yeah, and all other podcast apps where you can find
all other podcast apps.
Or your favorite ones, of course.
Favorite ones.
It's enough to listen to it in one app.
All right. Great.
Great. So see you in the next episode.
See you next time.